As I got from the introduction, my name's Nash. I am a developer relations engineer at DataStax. I'm very new at DataStax. I actually started last Monday. So I am kind of very eyes wide open and learning a whole bunch of stuff about the company right now. But what I can tell you is that they are building a stack for all of you to build the best generative AI applications with. I'm not going to talk about generative AI in this talk, unlike many others I've also seen as part of the conference so far. But just check out DataStax, check out AstraDB for what you can use it for to build your own generative AI things. Again, my name's Nash. I'm from Melbourne, Australia, although originally from the UK. And if you ever want to find me, ask me questions, follow me, follow what I'm doing online, I'm effectively Phil Nash all over the internet. On Twitter, LinkedIn, whatever social media network you might be using at the time. So, we're talking today about conquering complexity in JavaScript applications. I've written plenty of JavaScript applications myself, including the one that, was about the world's favorite sandwich filling. That was a period of time where the company I worked for at the time didn't have any clients to do any work for, so we built weird stuff instead. It was good stuff, although terrible JavaScript, I'm sure, and that's what we're going to try and solve today. I want to start by kind of talking about complexity and what that kind of means. I think our jobs are complex. As developers, as software engineers, we are tasked with the job to take the real world and then model it back on a computer. Take the real world, take everything that's around us almost, and model it back in a language, in a programming language. Again, one of my favorites is JavaScript, and that's why this talk is kind of based on that. And sort of abstract away the complexities of life and business problems, and do so in a almost human language, effectively. And that's hard. And so therefore, code itself is actually inherently complex. It's difficult to take those complex problems that we have to deal with and then translate them into something that we can continue to understand. And what I really mean by that is that complexity exists in the business problems that we're trying to solve anyway. What we need to avoid is adding additional complexity to that. And that is it's not necessarily what our languages, programming languages, are adept at helping us with. We have to build our own rules and our own ways of dealing with that in order to succeed and build programs that we understand and can continue to maintain and build upon. And so it turns out that our job is to manage that complexity. Our job is to use the tools we have at hand to build applications that we can both work today and we can use today, but that we can maintain and build upon in the future. If we do not manage that complexity, then eventually it becomes way too hard to actually build upon the application, the code base that we've created. And that's what I want to help us avoid today. So I gave a talk last year, not at this conference, but a few other conferences, in which I dug into a bunch of data to find out what, according to static analysis, were the most common issues in JavaScript projects. And this was our top 5. It turns out that many of the problems in JavaScript projects, at least those detected by static analysis, are ones that are relatively trivial, perhaps. The idea that leaving commented out code in a code base is a problem it depends on your kind of belief of what a problem is. I think commented out code in a code base just confuses things, and thus it does make it harder to read what a function does. But it's not going to break your application. It's not going to make things too much more difficult in the future, and it's very easy to delete commented out code. But it turned out that number 2, our second most common issue, was that the cognitive or the complexity of functions in our JavaScript projects is just too high. And that is a problem, because as I said, managing complexity is our job. Therefore, if the second most common issue in JavaScript projects is that functions are too complex, then as an industry, perhaps we're not quite doing our job as well as we could do. But we're here to fix that, right? But that begs the question, right? What's too high? I can kind of say that your code is too complex. It's the complexity of it is too high. But what does that really mean? That's what I'm going to get into next. How do we measure complexity? Does anybody have any ideas of measuring complexity, how you do so in your own code bases. Feel free to shout out. Has anybody heard? Oh, sorry. Maybe I can show you a piece of code. Hopefully you can read that. It's not very readable. This is a JavaScript function that sums up prime numbers underneath a number that you give it. And so it has a couple of loops. It loops through the numbers. It loops through making sure that the next number underneath it is a prime number. And if it is, we add it to the total. We get a sum of that. And we get this two nested loops, two conditionals. But how complex is it? It's sort of difficult to say unless we have some kind of measure for that. And me showing you a function and just saying, is this complex? Doesn't help. How complex is this? This is a function that gets words. You give it a number and it returns, it's a big switch statement that returns 1 if the number's 1, and it returns a couple if the number is 2, and then a few and many and lots. And this, I would say, is not very complex. It's just a switch statement. It's just checking one value. But like not very complex is not a useful measure either. Give me a hands up if you've heard of the term cyclomatic complexity before. Yeah, okay, cool, a few. And for those who haven't heard, cyclomatic complexity was a measure that was invented in 1976, so it's getting on to almost 50 years old. It is a way of measuring complexity in code by giving functions or classes a score based on things that happen within that code. So in cyclomatic complexity, you measure that score by increasing the score every time you hit sort of a break, a branch, a loop, or a conditional. And so in this sum of primes function here, it scores 1 for being a function in the first place. Like every function is a minimum cyclomatic complexity of 1. But then as we hit the first for loop, we add another 1. We hit the second for loop, there's another 1. We get a conditional inside that, and that's another score of 1. And cyclomatic complexity scores 1, finally, for the conditional at the bottom. Ultimately, a score of 5. That is a way to measure the complexity of this particular function. However, cyclomatic complexity when applied to our getWords function, which is that big switch statement, scores 1 for being a function, and then 1 for each of the cases that are in that function as well, ultimately scoring this function 5 as well. Now, I would argue again that this little switch statement here is a lot less complex than our sum of prime numbers, which does nested loops and conditionals. It's much more confusing. So can we do better? See, cyclomatic complexity itself actually just measures the number of different paths through a system, through a function. That's why every time you break or loop, that's why it's increasing a number. When you measure the number of paths, that complexity score actually also gives you a number of tests that you'd need to write in order to fully cover that function with tests. And what's really more important to me, at least, in this world of like dealing with complexity, is how we as programmers, as developers, understand a piece of code and how well we can work with it. And cyclomatic complexity is not doing a good job of measuring that. It's not to say it's a bad measure, it just measures different things. Has anybody heard the term cognitive complexity before? Fewer people. Okay, good, we're in the right room. Cognitive complexity was a term invented in 2016, so it's only 8 years old. It was invented by the fine people at Sona, who are behind tools like Sona Cube, Sona Cloud, and where I was working before I started this job 2 weeks on Monday. Cognitive complexity creates a score for a function the same as cyclomatic complexity does, but it scores it differently. And it scores it to be more akin to how we are understanding that code as a developer, how we try and read that code. So it does so by incrementing the score by breaks in flow, so conditionals and loops again, but it also increments in the back of its head a nesting score. And when you are nested within things, a function, a conditional or a loop scores both 1 plus the current nesting score. And so what does that look like? Oh, when we come to our sum of primes function, we no longer have to score 1 for being a function. You can have a cognitive complexity of 0 if your function is just entirely linear. And I appreciate that. Just reading a function from top to bottom without having to jump all over the place doesn't tax one's mind too much. But then we hit our first loop. we score 1, and in the back of the mind, cognitive complexity adds 1 to the nesting score. We hit the second loop, so we're nested once, so we score 2, and we add 1 to the nesting. We hit the conditional, which is now nested twice and scores 3 points for that. And then we do a bunch of like dropping out of things. So we drop out of the conditional, we take 1 off the nesting. We drop out of the loop, we drop 1 off nesting. So nesting score is now just 1. And so our next conditional scores 2 for being nested once, and then it all finishes off again, eventually scoring 8 for this. Complexity of 8 is actually not too bad. I guess there's not too many lines here, but it does capture the fact that we have to consider 2 loops, 2 conditionals. We've got some looping variables that we have to keep an eye on and keep in our minds as we're dealing with this. And reading through this is a little bit more complex than, say, reading through our getWords function, our big switch, which scores a solid 1 for being a switch and gets on with it. And I think that captures, at least in that comparison, a much better idea of what is complex for us to understand as a developer, rather than just how many different paths we have to go through a function. And so using this, we can apply it to our code and work out where the complex parts are for us, for our maintainability. See, I actually think, so I didn't come up with this score, and I only worked at Sonar for just over a year. So back in 2016, when they were coming up with this, this was not their mental model, but this was my model of it. It's this idea of, like, as you're reading through things, you've got kind of a stack that you're dealing with in your brain. And as you nest things more deeply and more deeply, you always have to keep considering what you're nesting, what the conditional or the loop you're currently within is. And as they build up, it's fine when you're in just one for loop. That's great. You know you're just looping through a list of stuff. But then when you're looping through 2 lists of stuff, that is kind of increase the complexity. It increases it because that inner loop runs as many times as the outer loop has to run. Times as many times. I times J. And then you get inside that conditional, and you're having to deal with, our outside loop, our inside loop, a conditional, and that is just adding things on top of this brain stack. Now, you do get to pop things off at some point and put things back on, and so thrashing about in terms of that stack as well as also adding to the complexity of things. And only once you kind of clear it all off, you can kind of breathe a sigh of relief and go, great, I got through that meaning, I got through that function, thank goodness. But the higher that stack goes, the more you have to keep in your head to understand what is going on in the context of the current line of the function you're reading. And that is something we can improve. So that brings us to conquering that complexity. I'm not just here to tell you that your code is way too complex and you should do something about it. Well, I am, but I've got the rest of the talk is what to do about it. So hopefully you can join me on that. When we want to conquer this complexity, we can find out about it in 2 ways. In many ways, sorry, in a few steps. First part is we have to understand where that complexity is. Now, I've shared with you this idea of cognitive complexity, a score that we can apply to functions to see what a sort of industry-specific score can tell us about that. But we actually need to understand where that complexity is within our own projects. And so for that, I'm just going to jump out. I have a project open here. This is the TypeScript adapter for the AstraDB API. So AstraDB, as I said, is from DataStax. It is a database. It's a vector database. It has a bunch of stuff to it. And so I cracked open the open source code for the adapter for this and tried to find what I thought was the most complex function there wasn't there. Now, I don't want to get in trouble here. It turned out not too many of the functions were too complex, so I took the most complex one and then made it worse. Just to help illustrate the problem here. So if anybody from DataStax ever sees this, I'm very sorry. The code is better than this. It's my fault. So I took the insert many function. Insert many is just going to take a bunch of documents and insert them into the database. But it does a couple of extra things with that. Since we added a vector store to AstraDB, insert many kind of can take this options object here, which might come with a bunch of vectors, and then they need to get mapped up to the documents and then inserted. And there's a couple of ways we do that, which is why it had some inherent complexity to it. To show the complexity in this, I have installed SonarLint. Sonalint is a free IDE plugin that will lint your code in 30 or so languages. It works in many of them, and indeed has cognitive complexity scores in many other languages as well. So if you're working not just in JavaScript or TypeScript, it's going to help you in other languages as well. And what we've got here is an underlining for this function insert many. And the underline says we need to refactor this function to reduce its cognitive complexity from 34 to the 15 allowed. I promise you it wasn't 34 in the first place. Again, I made it bad. But what this says is that Sona believes that the kind of threshold for a complex function being, or a function being too complex, is about 15. I think that's about right. That sum of primes function we were looking at, it's got some nesting going on there, but ultimately scored 8 because it's not too long and it wasn't too complex. It was understandable. It was nice to illustrate the difference between that and a switch statement. This is now 34. That's probably a problem. Numbers like this, hard kind of thresholds like this, are kind of difficult to necessarily agree with. You might decide you want something different in your team, but I actually think 15 is quite good. 15 is actually a little bit higher than I'd be comfortable with. But what I like is that when you hit 15, it gives you a really good reason, a really good excuse to stop and think about this function as you're writing it, or if you come across this in some legacy code. It's a really good reason to stop and think, can we break this up and make it easier to understand for the future? And when you do, you don't just get it to just below 15. You can bring it down to as lower complexity as you possibly can. And the rest of the talk goes into that. Another useful thing about Sonalint in this case is that if you scroll all the way down to the quick fix section, it can tell you all the locations in which we've added complexity, all the locations that we are nesting and adding scores to it. And you can kind of see here, I've got this big if statement which actually goes around the majority of the function. It goes all the way down to there. There's the else at the end of it. And so that scores 1 for being an if, 1 for being an else. But now everything else is nested inside that. So the next conditional here is +2. This one is now +3. We eventually get to +4, which is, yeah, it's nested 3 times. Do we get a +5? Not, yeah, maybe. Yeah, +5. Cool. So like right here at this point, I've got way too many things that I'm trying to think about. It doesn't necessarily matter what's going on here, but I've got way too many things to think about before I throw an error, apparently. You know, there are some of the scores, a couple for conditionals, a couple for other conditionally things. But it's really nice to be able to see all the bits of the function, where they are scoring complexity, and when you find the highest bits, and if you kind of look down, it's very small on the screen right now, but in the bottom right there, it's got kind of all the line numbers and indeed the total score. So that 5 there is indeed the highest scoring piece of complexity, and probably would be the first thing you try to reduce. So yeah, Sonalint is really good for pointing out that when you cross this threshold of complexity and then showing you where that complexity is in the function so you can go and fix it. Next step is to do nothing at all, which is one of my favorite things to do when programming. If you have a piece of legacy code like this that you are now checking using cognitive complexity, then there's absolutely no point in changing anything that doesn't need to change right now. It's good to know and understand where that complexity is, but there's no need to, it would be a risk to actually change anything about it without needing to. Complexity is only an issue if you need to understand and maintain this code and change it for some reason now. And then part 3 becomes sort of cleaning up as you code. As you find these things, that as you are assigned a task or decide you need to change something or fix something, if you find you have an overly complex function, now it's time to sort of clean that up. If you refactor that function and refactor it first, you're going to get 2 things. Firstly, you're going to get a nicer function for the future. It'll be easier to maintain that entire project over the time. But secondly, it's going to make making the change that you needed to make easier right there and then. So you refactor first, and then make the change first. Then make the change second. And note that refactoring, hopefully is something you agree with me here, that refactoring is improving how the code works without changing what the code does. You should still be able to call a function and get the same output that you would beforehand, but you don't change the result, you just change how it goes about it. And so how do we know we didn't change the result? Hopefully you agree with me that tests are a good way of doing that. A really good way to gain the confidence that your code continues to do the thing that it did before you made a change to it. If you don't change the tests, but you do change the code, if the tests continue to pass, then your code is continuing to do the same thing as long as your tests are testing everything. Again, it is important in this case that when refactoring is changing how it works but not what it does, tests must test what the function does and not how the function works. If you end up with sort of test code that relies on the internals of a function, then changing the internals of the function is going to break that test, and that's not helpful at all. So you must ensure that you are indeed testing what the function does, and then changing how it does it to make it less complex. And so if you don't have any tests, that's absolutely step 0 of your refactoring. You cannot be confident that you haven't changed anything, you haven't broken anything, unless you can prove it. And I can't think of any other way to prove that than tests. And on that note, tests actually must cover all the existing behavior. You might have been assigned a bug, something to fix in this code, but if you're going to refactor the code, then your tests must cover what it's doing right now. We can't, if we change the tests and the code at the same time, we can't really know that we had what was happening beforehand. And so you must test the existing behavior even if it is wrong. Refactoring is a separate step to changing your actual implementation. And so once you have got those tests in place, once you're ready to go, it's time to refactor. And cognitive complexity quite clearly punishes nested code. As I've said, it builds up a whole tower of things on top of a brain stack that I like to imagine, and gets harder and more complicated the more we add on to that. And so reducing nesting allows you to reduce that cognitive load on your brain as you're dealing with it. And so we're going to have a look at some tips on how to reduce nesting in our JavaScript programs via different ways to refactor them. We'll be inverting conditions and exiting early, structural collapse, extracting helper methods, and then I do have a couple of tips about other just little JavaScript idiosyncrasies that are newer but really useful for reducing this nesting. So first up, inverting conditions and exiting early, I think is really useful. This goes to that big conditional that I kind of had around the insert many function. And that is absolutely one of the things I added in myself, because nobody is that silly. We have this big nested function, and we have this one conditional at the start which nests the rest of it in, and otherwise return this sort of basic object at the bottom. We didn't insert any documents, we didn't add anything in. And that's not useful to sort of nest and keep everything in there. But if you invert that condition, if we actually say if we start by checking that we don't have any documents, then we can immediately return, and otherwise we get on with the rest of the program. Returning early like this, I think, just allows us to stop having to consider what that conditional around the edge is for. Stop having to consider why we are nested so far in. It's just one thing sort of popped off the brain stack, if you will. If we invert a condition and return early, then we have just done with that condition, and we can carry on with the actual work that we want to do. Structural collapse is something similar. It is the way that we, if we find that we've got a conditional followed immediately by another conditional, then we can probably kind of combine those into just one. In this case, it's actually it sort of combines with the idea of an early exit as well, because in this particular bit of code, if our options has a vectors object in it, and the vectors object, the array of vectors is not the same length as the array of documents, then it's an error. We can return early. Otherwise, we carry on and we map up the vectors and the documents together. And so that error is effectively another early return. And so we can push those two conditions together, If we have vectors and the vectors are not the same length as the number of documents, then error and we get out of here. Otherwise, we can continue and we just go, okay, if there are vectors, then let's loop through them and add them to the documents. We could probably zip that up slightly better, but that's how it's written right now. So collapsing two conditionals into one, and in this case, allowing you to exit early, means that we have dropped one of our conditions here, and life has got a bit better. And it sort of pops off the brain stack. We have one less thing to consider. That's how I like to think about this. Extracting helper methods, I think, is one of the most useful parts of this. It's also the more difficult part, I think, because getting a helper method right is very important. And so in this case, we're actually looking at that second part of the code from the last part, in which now we have got vectors in this object. We're going to loop through them and assign a vector to a document. And here, so what we have here is a conditional, a loop, a conditional, and it would be better to do less of that. I don't like that we have to, within this code, check whether a vector exists at this part of the array. I feel that could be handled somewhere else. And so if we were to create a function like add vector to document here, we reduce the context of what's going on in this code. We reduce the context to just a document and a vector. And if that vector exists, then we return both of them together. If it doesn't, then we just return the document. And that standalone helper function is so much easier to understand than where we were before, which was, within a conditional that says, okay, we've got a bunch of vectors, and then we've got a loop saying, okay, we're looping through each of these documents, and then we're going to squish together if the vector is way too much. If we've reduced the context of that helper function to just the idea of a document and a vector, then adding a vector to a document is much simpler. Then back in the original function, we get rid of one of our conditionals because it's now handled by the add vector to document function, which is now named much nicer. We actually have a name for this piece of code. It's adding a vector to a document, which we didn't have before. We'd have to read it and understand what the code was doing. Now we can just sort of read the name, and it handles our conditional and our extra nesting for us. So helper methods allow us two things. We get to reduce the context within that helper method so that we could independently test that method. We can more easily understand what it does. And then we can name that method as well. And that naming means that means it's easier to read and understand without looking necessarily what's inside of it. I thought of a third thing. No, it's gone away again. Damn it. Extracting a helper method like that allows us to reduce the context, but also to add names to things. And it allows us to just pop something else off the brain stack. And finally, there's, like I said, there's some language features that are really going to help with this as well in our JavaScript. For example, if you are dealing with, and this is not an example from the code here, but if you are dealing with like a nested object, then you normally had to check that each kind of level of the object that you're going down existed before you can call into the next thing without, otherwise you end up with trying to call a property on undefined and the program falls apart. Thankfully these days JavaScript has caught up with modern stuff, and we have conditional properties which will return undefined as soon as something is undefined without breaking our code, and allows us to stop just adding Boolean operators just to dig our way down a nested object. And then secondly, and this is going a bit small again, but if you are kind of trying to set something only if it's not already been set before, then this is kind of an old way of doing that. We've got this chunk size, and what we want to do is set it to a default of 20 if it doesn't already exist. And now you can't just kind of check. You can't kind of Boolean like hit it with two exclamation points to see if it's a Boolean nothing, because if it turned out that chunk size was 0, then that would return a false for you, and you'd end up setting it to the default even if you meant to be 0 in the first place. So you instead check whether that chunk size is null or undefined, and then if it is null or undefined, we can set it to something. Otherwise, we can set it to itself, or a thing in an object here. And what's much easier is either if you're setting to a new variable like this, then we can use the nullish coalescing operator, that's the double question mark there, which is doing the same as, not undefined and not null. And if you're doing this within the same object, we get the nullish coalescing assignment operator, the double question mark equals, which allows us to, if you're setting it to something, it particularly works in a property on an object. If you're trying to set something that does already exist, then it won't do anything. And if it doesn't exist because it's null or undefined, then it will set it. All within this tiny operator here, and I love that. Double question mark equals, the nullish assignment operator. And what those things do means we don't have to, throw in a conditional or a nested or a ternary here in this case, in order to just pop things off the brain stack. I've got time for a little bonus rant, which isn't necessarily going to help with this refactoring, but I think is something that adds to the complexity of our applications without really any need for it. I'm not a fan of nested ternaries. Anybody out there fine with just nesting ternary kind of operators with each other? Well, no one's admitting it now because I said I didn't like it, but this has been kind of, I think we're at April now. It's not exactly news now, but back in the end of last year, back at the end of 2023, Prettier, the formatter, which I hope you're all using, it's a great formatter, but it came up with an experimental way to format nested ternaries. Now, this is because for about 5 years, Prettier stopped kind of indenting nested ternaries for a while. And then for about 5 years, there was a hundreds and hundreds of comments long thread on GitHub with people going, fix the nested ternary formatting. And lots of people with lots of different ideas and ways to nest ternaries or format nested ternaries better. And this was the thing they eventually came up with. This was their example code. And it's fine. But the real answer is to stop nesting ternaries at all. You don't need to format them if they're not nested, because then you don't need to read complicated things. I really dislike this bit of code because whilst, yeah, sure, it's sort of nested nice, it's formatted nice enough, it still takes me a while to, and I've given these slides before, but the animal name is, okay, if the pet can bark, then if the pet is scary, then it's a wolf, and why are wolves pets? I don't know. But if it's not scary, then it's a dog. Else, and the else is now, we're back out again. We're back into like it's else on the can bark. And if it can't bark, we'll test if it can meow. And then if it can, it's a cat. And otherwise, ultimately, it's probably a bunny. The wolf thing aside, I just don't like that. And it doesn't matter how you format this. I've never liked it. I think we can drop all nested ternaries. We can use some of those things that I've said already as part of this talk. We can change up the conditions and exit early. We can turn it into a function on its own, which means we can test it independently to ensure that this code will always do what we expect it to do. And I think, honestly, this reads much nicer. So in this case, we've got if the pet can bark and the pet is scary, then it's a wolf. Otherwise, we can stop worrying about if it's scary. If the pet can bark, we return dog. If the pet can meow, return cat, otherwise return a bunny. Like, I think that's easier to read, it's easier to test, and we don't have to deal with nested ternaries. And I know that some people will say that they are fine reading nested ternaries. They've got no problem with this kind of thing. They understand it immediately. But I don't think that's the case for everybody. I don't think it's the case for me. At least, there's one person that I know doesn't like reading these, and I bet there's more. And so all of this, all of what I'm trying to come to say to you today is actually not just about writing code for yourself to be better. It's actually about writing it for the next person. And that next person can actually be you, maybe in 6 or 12 months' time. My goodness, I dislike reading my own code from 6 and 12 months ago, and I wish I was better at that. But it could be you in the future. But it could just be your colleague. It could be somebody on your team now. It could be somebody on your team in the future after you've left that team, gone somewhere else, and they have no idea what you're thinking of. All of this is to say that nesting ternaries, nesting things too deeply, doing any of that is making it harder for other people to understand the work. And even if you can understand what you wrote right now, That's not necessarily going to be the case for the next person. And so kind of to recap on this, complexity is what we do all day. Every time we open up that IDE and write that next feature, fix that next bug, we are dealing with managing complexity. When I open up a project, sometimes I go in and add complexity just for fun, so I can talk about it later. But hopefully, we're mainly trying to not add to that complexity. Measuring complexity, there are many ways of measuring complexity. I really like cognitive complexity. It gets to that heart of what makes it easy to understand and build on a piece of code, not just how many lines. You can measure complexity simply by lines of code. If there's a 100-line function, a 10-line function, that 100-line function is probably more complex. Probably. But I think that cognitive complexity is one of the best measures I've seen for that. And it really kind of speaks to me every time I see that come up, every time I come across a function whilst using SonarLint that is across that threshold of complexity. And then finally, conquering it. Reduce the nesting in your code as best as you can. Nesting is absolutely the enemy. And we can do so by inverting conditions and exiting early. We can collapse conditionals down on themselves. We can extract helper methods, reduce the context that goes on in that helper method, and make it easier to read and understand the previous bit of code by naming that method well. And finally, by using some of the other bits of the language to help out. And just don't nest ternaries. There are better ways to deal with that. Just write it as ifs and elses even. It's so much easier to read a set of ifs and elses than a set of colons and a set of colons and question marks. I even say it wrong when I'm trying to talk about it. That's how bad. There are tools that will help you out with this, of course. I pointed out SonarLint, which again you can install in your IDE, and we'll tell you about both cognitive complexity in your functions, as well as many other kind of linting things for many applications, many languages. Then, if you want to kind of raise the game on that, then using SonarQube or SonarCloud as part of a pipeline allows you as a team to kind of dig into a bunch of rules that are going to make your code better. But of course, if you're just using JavaScript open source things, if you're using ESLint in your projects, then ESLint does not have a measure for cognitive complexity. It does have cyclomatic complexity, but it's not turned on. So you can use that. But if you would like to add cognitive complexity just to your ESLint plugin, so to your ESLint kind of set of rules, then Sonar actually also produces an ESLint plugin, Sonar.js. It has a bunch of rules, including cognitive complexity, which you can turn on as you like. And I recommend that. Like, if you already have ESLint, then just add the ESLint plugin, Sonar.js, get that cognitive complexity rule going, and see what it tells you about your code. And then, as I say, don't change anything right then. You don't have to fix that because you found out about it. But it does make you aware of it when you need to change something. You can work on that refactoring first. I've got two other links for you. There is a wonderful cognitive complexity paper, which was written by the people at Sonar back in 2016. I'm not normally one for reading computer science papers. But it turns out I've read this one 3-4 times now. It's really helpful. It goes into a bunch of the nuance of cognitive complexity. Cognitive complexity itself was written about Java in the first place, and includes some kind of appendices for JavaScript and for Python and things like that. And I do recommend reading it. And I also recommend reading my blog post, Stop Nesting Ternaries, which is just that rant, but in longer form with more examples. And then share that with all your colleagues and friends and anybody who's ever written a nested ternary. Other than that, that is all I have for you this afternoon. Thank you so much for joining me. It's been an absolute pleasure to be here. Again, my name's Phil Nash. I am a... I'm a developer relations engineer at DataStax, and it's been an absolute pleasure to be here. Thank you so much.